We have been looking for the last few modules on the analysis of count data. The standard model for count data is the log linear model. We have seen that the underlying assumptions for the log linear model can often be quite restrictive, and we have in detail considered the situation where the mean and variance equality assumption do not hold. There are some other ways in which the basic assumptions can be violated, and in this module we will look at one particular assumption, which is when the number of zeros in the count data are in excess of what would normally hold for the Poisson variable. We will identify certain situations where this can hold and see that this can be accommodated using a likelihood-based framework. The two common models for these situations are something called the ZIP model, which is the zero inflated Poisson model, and we will also briefly touch upon an alternative called the hurdle model. Finally, we shall see how these models can be fitted on a data set using R. The learning objectives for this module. First, we will look at some examples of zero inflated counts. Next, we will look at a popular likelihood-based method of modeling these counts called ZIP models or zero inflated Poisson models. We will briefly revisit an alternative means of modeling such data through the hurdle model. And finally, we'll look at some illustrations using R, including the syntax required to fit such data. We have considered several examples of counts in previous models. Let us consider some more examples. Firstly, the number of cigarettes smoked by students of a college, the number of insurance claims for a certain type of risk, the number of earthquakes by geographical location, and the number of incidents of domestic violence in a household in a particular month. Now, this set of examples is somewhat distinguished from the previous examples you have seen of counts, and the reason is that if you were to collect data on any one of these variables and to plot a histogram of the data, you might expect to see something like this. So the unique phenomenon about this histogram is that while it can generally be assumed to follow a Poisson distribution, the number of zeros for the data are considerably in excess of what we expect to see if we had indeed a Poisson distribution. Such distributions are called zero inflated count distribution. And in this module, we will look at some popular methods for modeling zero inflated counts. A seminal paper for zero inflated Poisson regression is due to Lambert 1992, which looks at zero inflated Poisson regression with an application to defects in manufacturing. It was published in Technometrics. Now, the zero inflated Poisson regression is a model which is intended for count data where zeros are in excess of what would be expected if the data followed a Poisson distribution. The example considered by Lambert is motivated by looking at manufacturing equipment. Now, when a set of manufacturing equipment is properly aligned, say this is done with probability P, the chance of defects is virtually zero. However, when the manufacturing equipment is not aligned, the number of defects can be assumed to follow a Poisson distribution with parameters, say, lambda. We may have different situations based on whether P and lambda are related or not. In fact, both of P and lambda may be related to sets of covariates which may be identical or distinct or overlapping. We could have situations where P and lambda are functions of each other or unrelated, and these are situations which Lambert has visited in her paper. So here is a plot of the raw data from the paper due to Lambert. This looks at printed wiring board data. Components are mounted on printed wiring boards, and the experiment was conducted at the AT&T Bell Laboratories and looked at 5 factors for their influence on solderability. The 5 factors being mask, opening, solder, pad, panel, all of the covariates being categorical. And the box plot here shows the number of defects on one of the 25 boards in the experiment. The boxes are labeled by the board factors. When the box is degenerate, as happens for example for the leftmost board, it corresponds to a situation of 0 counts. Lambert looks at some likelihood-based means of modeling this data. So the zero inflated Poisson regression model assumes that we have responses y equal to y1, y2, yn say, which are independent, such that yi follows 0 with probability pi, and it follows Poisson lambda I with probability 1 minus pi. This means that the probability of yi equal to 0 is given by pi plus 1 minus pi e to the power minus lambda pi, and you can see that this is in excess of what would happen if yi just follows Poisson with probability rate parameter lambda I. So thus yi follows a distribution such that yi is equal to 0 with probability pi plus 1 minus pi e to the power minus lambda I, and equal to k with probability 1 minus pi e to the power minus lambda I to the power k by k factorial for k equal to 1, 2 and so on. We have 2 sets of parameters, the lambdas equal to lambda 1 to lambda n for the n observations, and p equal to p1 to pn, and these satisfy log of lambda equal to capital B into beta, and logit of p equal to log p over 1 minus p component wise is equal to capital G into gamma, where B and G are known covariate matrices. Now the covariates which affect lambda may or may not be the same as the covariates which affect P. That is, the covariates which affect the imperfect state may or may not be the same as the covariates which affect the probability of the perfect state. We could, for example, have situations where B is equal to G, in which case zip regression requires twice as many parameters as Poisson regression. At the other extreme, we could have a situation where the probability of the perfect state does not in fact depend on covariates. In this case, G is a column of 1s only, and zip regression requires only one extra parameter than Poisson regression. We could also have intermediate situations. For example, if the same covariates or a subset of covariates affect both P and lambda, we can try and reduce the problem by modeling P as a function of lambda. It turns out that the computation speed depends considerably upon these assumptions. First, let us look at the case when lambda and P are not related. that is not functionally related. The observed data likelihood is as given in the left panel on this slide. The sum of exponentials in the first term makes direct maximization of this expression difficult. But suppose we knew which zeros came because the setup was in the perfect state, and we knew which zeros came because it was in an imperfect state. That is, we know which zeros come from the Poisson distribution. So this is equal to assuming that we have observed another covariate Zi, which is equal to 1 when Yi is from the perfect zero state, and Zi equal to 0 when it is from the Poisson state. So if we had information on Zi, the likelihood would be given by what has been termed the complete data likelihood, and this is given on the right panel on this slide. Now from the terms observed data likelihood and complete data likelihood, you can guess that this is a situation for the EM algorithm, and Lambert in her paper works out the details of the E and the M step required to maximize the likelihood in this situation. The case where P is a function of lambda, the log likelihood for the zip model can be written up to a constant by the expression given on this slide. Now the EM algorithm is no longer useful because beta and tau cannot be estimated even if Z is known. That is, they cannot be estimated very simply. So this is a situation for the Newton-Raphson algorithm, and the steps of this algorithm have been worked out by the author, and she presents the estimates together with their standard errors and confidence intervals. So having worked out the theory, the author presents an application of the zip model to her data. Her model is given by specifying log lambda equal to panel plus pad plus mask plus opening plus solder plus the interaction mask solder plus the interaction opening solder. The probability of the perfect state is given by the model log of P over 1 minus P, that is the logistic model, equal to panel plus pad plus mask plus opening. Now note that the formula here is written in the sense of an R formula. She has also presented the estimates, the standard errors, all by using properties of the corresponding likelihood. She has fitted several alternative models and presented the values of the log likelihood so as to be able to choose between these models. The zip model can easily be fitted in R. However, it cannot be fitted using the base package of R. Instead, it is necessary to use the PSCL package. The zip model can be fitted by a function called 0INFL. So here is the syntax of the 0INFL. The formula describes the count regression relationship of y and x. The model likelihood can be specified by the distribution and link arguments. The first determines the count distribution and is Poisson by default, but it could also be set equal to negative binomial or geometric, for which the log link is always used. The zero inflation component is always binomial, with the link function as specified by link and defaulting to logit. ML estimates are calculated using the optim function in R, and the controls can be set using the function 0INFL.control. Starting values could either be user supplied or estimated by the EM algorithm or by glm.fit, which is the default value. The returned fitted model is of class 0 INFL, and it is a list which is very similar to the GLM object. So some of the elements such as dollar coefficients or dollar terms are again lists, and they behave very similar to the corresponding GLM components. The standard extractor functions for the fitted model is available for objects of the class 0 INFL, and these include the usual summary, which will provide the partial wall test for all the coefficients. Note that there is no ANOVA method, but the general coef test, wall test, linear hypothesis functions will all work on the 0 INFL object. So here is an example of the application of the 0 INFL function. This has been applied here to an example taken from the R website on zero inflated Poisson regression. It looks at data on 250 groups that went to a park, and each group was asked about how many fish they had caught. Now, as some individuals did not fish, we obviously expect an excess of zeros. The covariates are how many children there were in the group, how many persons there were in the group, and whether or not they had bought a camper. So here we see the results of the zero inflated model fitted to this data. Now, application of the zero inflated model by itself does not tell us whether it has led to any significant benefits in the sense of whether it has led to any improvements over the GLM model. This can be tested formally using something called a Wong test. So this has been done in this slide. P1 is the object which fits a GLM, the standard GLM with the log linear model to the data. M1 is the object which fits a 0 INFL model to the data, that is the zip regression. Having fitted these two models, we can type Wong P1 and M1, and this will perform a test of the non-nested hypothesis comparing these two models. We see here that the value of the test statistic is minus 3.574, and the p-value is 0.0001, which suggests that there has indeed been a benefit due to using the zero inflated model to model the data. Very briefly, an alternative class of models for this data is the hurdle model. The hurdle model is also a two-component model, but it does not model zeros from mixed sources. Instead, it uses a truncated count component for the positive counts and a hurdle component for the zero counts. So formally, the hurdle model is given by a probability mass function which is equal to f0 if y is equal to 0, and 1 minus f0 times the truncated f count over 1 minus f count 0 if y is positive. The corresponding mean regression relationship is given by log of mu equal to xi prime beta plus log of 1 minus f0 minus log of 1 minus f count. This can be fitted in R also by using the PSCL package and the hurdle function. The syntax of the hurdle function is as given on this slide, and you can see that it is virtually identical to the zero INFL function. For more details about the hurdle model and to get a good overview of alternative regression models for count data, I refer you to the model on regression models for count data in R by Xilis et al. To summarize, the standard Poisson assumptions may not always hold for count data. In this module, we have looked in detail at the situation where the number of zeros for counts are in excess of what would normally hold if the Poisson model were assumed to fit the data. This can arise basically when the data can be considered to be a mixture of two distributions, one of which is discrete at 0 and the other is a Poisson, or if appropriate, a negative binomial distribution. These can be accommodated in a likelihood-based framework using something called a zip model, which is the zero inflated Poisson model, and the hurdle model. We have seen briefly what these models imply, how inference can be performed for this model, and briefly some simulation-based evidence for the performance of alternative likelihood-based procedures for the zip model. We have also seen that these models can be fitted using the PCSL library in R.